This is the full section of the variable acceleration chapter, and this is about using integration. Now, in the last section, we were using differentiation, and maybe we had S or X, to represent the displacement. We differentiated that to get, let's say, the S dt, or that might be the x dt, and that gave us the velocity. And then we differentiated again and did the v dt, or that's the same as differentiating the function of t for the displacement twice, and we get the acceleration. Okay, so going across this way was differentiation. I'll just put diff for differentiation. So it makes sense, if I want to work backwards, then we're going to integrate, yeah, because that's the reverse of differentiation. Okay, so what does that mean? That means if I start with acceleration and I integrate the acceleration with respect to t, I'm going to get the velocity plus a constant of integration. Or if I integrate the velocity with respect to t, I will get a function for the displacement plus a constant. Yeah. Now I'm going to use C1 here and C2 because these are not the same constants. Yeah. And often in the question, you will need to find the constant before you move on. So for example, let's say we've got the acceleration and we need to find out what the displacement is. Then when we integrate our acceleration, we'll find C1. There'll be something in the question that helps us work out what C1 is. Then we can move on. And then when we get the displacement, again, there may be some phrase in the question that helps us work out what C2 is. And then we can then substitute that in. Now, let's say, for example, there wasn't anything in the question that allowed you to work out C1. Well, then what you would have at the very end here is something slightly different. Your velocity would be S, your displacement, plus C1t, because you've got to integrate that constant from the previous one, plus C2. So that may be something you need to do. Now, how are we going to know? What clues are we going to have in the question that help us find the constant of integration? Okay, so it may say something like initially at the origin. Okay, so what that means is that when t is 0 initially, s or x was 0 initially at the origin. If it says something like initially at rest, or it says for a particular time it's at rest, what that means, in this case, t is 0, v is 0. Again, we can use that to find the constant. Now, it may not necessarily be initially either of these here. It may be at a different time. So may be at a different time, which is fine. We just take that time and the velocity and we substitute it in. So look for those clues, underline them, write them down. That's going to help you work out what you need to do and to find these constants. Okay, a particle is moving on the x-axis, so it's moving in a straight line. At time t, the particle is at the point where x equals 5. I'm going to underline that. That's going to be useful. I'm going to write down when t equals 0, x equals 5. So that's going to be useful. the velocity of the particle, so we're given v, where time is greater than or equal to 0, so no negative values of t, is given by that. Okay, 6t minus t squared. Find an expression for the displacement of the particle from O at t times seconds, right? Okay, so first thing, let's write down v equals 6t minus t squared. Okay, so if I integrate that with respect to t, that will give me an expression for the displacement. Now we're using x for displacement in this question because you see it says when x equals 5, so it's going to be x, so that's going to equal, so we add 1 to the power, divide by the new power, so that's going to be, we'll tidy this up in a minute, 6t squared over 2 minus t cubed over 3 plus c. Okay, let's just tidy it up a bit. So we have 3t squared minus a third t cubed plus c. So that's what x is. Now look, we were told this at the start. We can use that to find c. So when t equals 0, x equals 5, so you can put so, that will give us 5, so this is x, isn't it? 5 equals 3 times 0 squared, so we just substitute 5 and 0, minus a third times by 0 cubed plus c, which then tells us that c equals 5. So our full expression is going to be x equals 3t squared minus a third t cubed plus 5. And this is in meters. Yeah. So I'll stick that in brackets. Part B. The distance of the particle from its starting point when t equals 6. So all we do here is substitute t equals 6 into the expression, so we can write down t equals 6, or when t equals 6, x will equal 3 times 6 squared minus a third times 6 cubed plus 5. So obviously you've got to get part A right. If you don't get part A right, then part B is going to be wrong. So that's 3 times 6 squared minus a third times 6 cubed plus 5, and I get 41 here. Now we need to think, what does this 41 mean? Is this the final answer? Now it's easy to miss this out, but it did say that at t equals 0 it was at the point 5. Okay, so I'm going to say this, but at t equals 0 x equals 5 meters, so it was already that distance anyway at the start, so you could think of it as like this. At t equals 0, this is where it was. Now at t equals 5, no, sorry, at t equals 6, it was at 41. The distance is this, not 4, 41. So our final answer is going to be when we do 41 minus 5 to get an answer of 36 meters. So it's easy to miss that out. So we need to consider where it was at the start. It's not always at the origin at the start. So don't forget to consider the position at t equals 0. Okay, it may not be x equals 0 or s equals 0, so just be aware of that. Yeah, that can catch you out. and you could lose a mark or two if you don't spot that in the question. Okay, a particle travels in a straight line. After t seconds, its velocity v is given by this here, v equals 5 minus t squared, again, where the time is always positive. Find the distance travelled in the third second of its motion. Okay, there's two things I need to point out here. The first thing is that if I had a velocity time graph here, with constant acceleration, I end up with these graphs which are sort of triangles, trapeziums, things like that. With variable acceleration, you're going to end up with a graph like this, but something is the same for both. If I work out this area here, okay, let's call these A and B, that area represents the displacement, the distance travelled. Okay, so area equals distance travelled. Yeah, and previously you did questions where, you know, it was SUVAT and things, and you had a velocity time graph, and to work out the distance travelled, you worked out the area of a trapezium or triangles or rectangles. But on a question like this, if this is it's basically going to be a function of phi equals some sort of function of t, isn't it? Yeah. Now, how do I find that area? Well, we know how to find the area under a graph. We use integration. So if I integrate the function of t for the velocity between the limits of a and b, that will give me the distance travelled. So the way that we're going to do this bit of the question is we are going to use integration. Now, when we use integration, there's one thing we've got to watch out for, and that is if the velocity graph does something like this. It goes below the axis. And let's say, for example, I needed to work out the distance travelled, and this was B, and this was A. Well, I can't just integrate between A and B, because bits are going to cancel out. I will need to work out this value here. I will need to integrate this bit, yeah, between the limits, and then I will need to integrate this bit between the limits, reverse the sign of this, the first integration, because I'm going to get a negative answer. Okay, and then I would need to add the two parts together to find the distance. For displacement, it may be slightly different because we'd probably just we'll take it as a negative, but in terms of distance, distance isn't the same as displacement. We would basically need to reverse the sign of the bit at the bottom. So when we do this question, we need to check that our graph isn't doing that. We need to check that we don't end up going below the axis, which we'll do in a moment. And then the second thing is it says here the distance travelled by the particle, so not the displacement, in the third second of its motion. Now, let's think about this travelling along in this straight line. So here is the time, 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. Right, we need to understand what it means by its third second. Right, this bit here is the first second of motion in its first second. So it's not actually at 1 second. It's all the time up to 1 second. This bit here is the second second. So the second second starts at the first and goes to the second. The third second of motion is here between 2 and 3, and if we were carrying on, the fourth second of motion would be here. So this tells us that our limits in our integration are going to be 2 and 3. The third second of motion is between the second and the third second. So the first thing we're going to do is this: check to see if v equals 5 minus 3t squared crosses the axis, crosses the t-axis between 2 and 3, because if it does, we're going to have to do what we just talked about there. Right, so one way to do this is actually to see where this actually crosses the t-axis, and that will be when v is 0. So let's try at v equals 0. So this is the t-axis. We'll get 5 minus 3t squared equals 0. So that will give us minus 3t squared equals minus 5, which will give us t squared is 5 over 3, which means it crosses the axis at either plus or minus root 5 over 3. Now let's work out what that number is and see if it's between 2 over 3. So square root 5 over 3, press the SD button. So it's actually either plus or minus 1.29. That's the three significant figures. Right, so the answer to my question is no, it doesn't. Yeah, it actually crosses the axis at the number 1.29 and negative 1.29, so that's fine. So because it doesn't cross the axis, I can now work out what the distance is by integrating. So now I'm ready to integrate between the limits of 2 and 3 of 5 minus 3t squared dt. So there's going to be no constant of integration. This time when you have limits, it's definitely integration. So integrating, I have 5t minus, then I'm going to have 3t cubed over 3. My limits are going to be 3 and 2. Let's just simplify that a bit. So 5t minus t cubed, basically, between 3 and 2. Right, so that's going to be 5 times 3 minus 3 cubed minus 5 times 2 minus 2 cubed. Right, so let's work that out. So 5 times 3, 15, minus 3 cubed, which is 27. So I'll get negative 12 from the first bit. Minus, then I'm going to have 5 times 2, which is 10, minus 2 cubed, which is 8. So minus 2. So I end up with minus 14 meters. Now that would be a displacement from the start, but I want the distance, so the distance is going to be 14. So I could say, well, displacement equals negative 14. So displacement's like velocity, it gives you the direction as well, which means the distance, and the distance is the magnitude of the displacement. So it's going to be 14 meters. So 14 meters is the distance travelled. Right, you should now be able to do exercise 11D on pages 189 to 191. So just as a quick recap, we integrate our acceleration with respect to t to get a velocity, then you're going to have a constant. If we integrate our velocity with respect to t, we're going to get our displacement. Now that may be s, that may be x, plus a different constant to the first one. If we want to find the distance travelled, we're going to integrate our velocity with respect to t, okay, and this is going to be the distance travelled between times a and b, between times a and b, and that will give us the distance travelled. So remember, there's no constant of integration. We have our limits, but when you do this, the thing you need to check for is to check if the graph of v equals the function of t crosses the t-axis, or it may even be the x-axis, or I'll just put crosses the axis. Yeah, you'll need to check that, because if it does, and you do your integration, you're going to have to do the two bits separately for the distance. Okay, so you're going to have to do this bit here, maybe this bit here, do them separately.